Hola clase! Today we are learning how to find the optimum solution when there are actually multiple solutions. As usual, I give you a step-by-step how to guide, and then we make an example together. The optimum solution is the one that maximizes or minimizes a specific function within the range of the feasible region. So before actually dealing with multiple solutions, I need to know how to find the optimum solution and how to interpret gradients. Now for our how-to, first you proceed normally to find the optimum solution. You may not know yet that they are multiple. So first you graph your inequations to find the feasible region, then you find the vertices, and you can do that algebraically or with a graphing program, and then you evaluate the function at the vertices. Before, one of those vertices could have had a maximum value, but now you're going to find that two vertices return the same value. That means that the inequation which is common to them has the same gradient as the function you're searching for. So it's actually one of the possible parallel lines. That means that all the points in the boundary within those two vertices are valid solutions. Let's see that in an example. Here they ask me to find the point that maximizes this function in the feasible region defined by these inequations. So we're going to start graphing our inequations, and again we're going to do it using GeoGebra. So I go to the graphing calculator, and I've already here graphed the inequations and the equations that set the boundaries, because we've got a video on how to do it, so you can check that as well. Now the last step now it's actually go and find the intersections or vertices of that feasible region. I find the intersect, position myself relatively close, and I see they're labeled, and here in the commands I see the coordinates, and I repeat the process going always in the sense that I decide. For me it's clockwise until I have them all, and I see them here labeled B, C and D, and here in the commands I can see the intersections, and you see that one of them gives me lots of decimals, and it's fine. I will just decide when it's sensible to round, but it didn't take me longer to do with GeoGebra. Once I've got all these four vertices, A being 3.8, B 4.5, 3.5, C to 1, and D I'm going to round to 4 decimals each. So I'm going to go 0.1428 and 6.5714. Then I can evaluate each one of them, which is substituting the x and the y coordinates within the function. If you do all that, the function of A gives you 20.7, function of B gives me again 20.7, and here I already see two values repeating, so I'm going to keep my eye on that. I go function of C, and again I substitute the values of x and y. That gives me minus 0.3, and the function of D, f of D, gives me again minus 0.3. So if I search for the maximum value, I actually have two options. A gives me 20.7 and so does B. So now what that means, if we go back to enlarging this graph, means that this line that actually sets the boundary of the inequation, that it's common to both A and B, it's actually a parallel line to the function that we need to evaluate. So all the points that are actually within A and B, forming part of the feasible region, are actually valid solutions. The way to write that is to make a statement, which looks very similar to the one we did in the previous video, but I need to specify that that function, f equals 2.1y plus 6.3x minus 15, has the same gradient as the line y plus 3x equals 17, which is the common equation. That means that all the points in the line between 3.8 and 4.5, 3.5 maximize the function with a value of f equals 20.7. And if, when I'm evaluating vertices for a multiple solution, something like that happen, I can always follow this format of statement where I give the function that I needed to evaluate. I tell that has the same gradient as whichever is the common boundary, and then I give which 2 points marking the feasible region, A and B in our case, and which is the maximum value. Once I do that, I will square it so it's easy to find, and I'm done. Now it's your turn to go and practice. Thanks for watching.